Okay. Okay, so this is Rachel. I am recording my Module 3, and it's going to be on binomial logistic regression. I'm going to be using multiple predictors. I wasn't sure if you wanted us to do single and multiple predictors, but I was hoping that it would be fine, and that any information that I would be including with a single predictor would also be incorporated with a multiple predictor. So I'm going to be using one of the data sets that you provided us with. So again, thank you so much. That was very, very helpful, not to worry about creating our own data sets. Okay, so what I'm going to be doing is talking a little bit about logistic regression and what it's used for, and then interpreting the output. So according to the SPSS help feature, which was in fact helpful, logistic regression is really going to be useful in situations that we want to predict the presence or absence of an outcome based on the independent variables that we're incorporating in our model. So it's similar in this way to linear regression models, but it's going to be a better fit when our dependent variable is dichotomous or categorical. In this case, it's going to be dichotomous because I'm doing binomial logistic regression. So logistic regression coefficients are going to be estimates of odds ratios as opposed to ordinary least squares like it would be for linear regression. And the estimate of odds ratios is going to be for each of the independent variables in the model. So what happens with logistic regression is it basically violates a bunch of assumptions with ordinary least squares. So I'm going to scroll down and look at some diagnostics. So if we're looking at this QQ plot of the normalized residuals, so with ordinary least squares, it's going to be really important to have this not happen. So we can see right off the bat this is violating a bunch of assumptions. For example, normality, where the residuals should be normally distributed and clearly are not against the line. It's also going to be violating linearity, where it should be following the line in a continuous manner, and there's clearly a break. When we're looking at the detrended QQ plot, we're seeing that there's obviously patterns. So normally we would see this kind of cloud, evenly distributed, no particular patterns. If we're going to say that we weren't violating assumptions, but we clearly are violating the assumption of homoscedasticity, for example. So the assumption of homogeneity of variance is being violated. So ordinary least squares, not going to be a good fit, so we're going to have to transform our numbers in a different way. So what we do is we use the odd ratios or the exponentiated b's that we're going to be talking about, and by we I mean me, that I'll be talking about later. We're going to create natural logs, in this case log odds, and that's going to transform the data so that it's continuous and it has this sigmoid, I think it's pronounced, kind of S-shaped, continuous kind of plotting of the dependent variable. So before I kind of go into describing the output, I am just going to highlight from one of the articles that I read to kind of help better understand this material. Karina Mood wrote an article on logistic regression called "Why We Cannot Do What We Think We Can Do and What We Can Do About It." And she was really highlighting some of the problems that happen when we're relying on logistic regression to interpret information with dichotomous outcomes without really understanding the limitations. So a lot of times people that would just be using linear regression are going to be using logistic regression when their outcome is dichotomous or categorical, but they don't really understand that it's a different transformation with a different set of complications. So one of the things that she really highlights is that when you have omitted variables, or what she calls unobservables, it's going to have a really big impact on logistic regression in ways that you might not necessarily be able to anticipate just from having an understanding of linear regression models. So unlike with ordinary least squares, the omitted variables affect coefficients in logistic regression regardless of whether the unobservables are correlated to the independent variables or not. So because the coefficients depend on both effect size and the magnitude of the unobserved heterogeneity, the results aren't going to be as straightforward to interpret as they are with linear regression. So just one of the things that this made me think of was with, like, when we're running diagnostics for a linear regression model, one of the things we're looking at is homoscedasticity with the detrended normal QQ plot. And so if we see patterns in a general linear model, we're going to assume that there's some type of a variable that is going to be impacting our residuals that are not accounted for in the model. And so we're going to say that we need to find that additional variable, or kind of assume that or see that the assumption is being violated. But with logistic regression, because the unobservables are going to impact the model regardless of whether or not we see a correlation between the unobservables and the independent variables accounted for in the model, it's really important to make sure that we include all of the independent variables that are going to be statistically significant. So she has a couple of suggestions in the article about how to address these problems if we're using logistic regression, but she really, really emphasizes that when you're collecting data, so you're at the experimental stage, really try to collect continuous data if possible, or at least ordinal data, and that if you have to use logistic regression, just really try to make sure that you have all of the independent variables that you need to. Okay, now I'm going to actually move on and talk about the output. In this model, I regressed y onto x and x2, where x and x2 are both continuous variables and y is a dichotomous variable, our outcome. And just looking at the correlations, I want to see if there's a positive relationship between our independent variables and our outcome, our dependent variable. And there is. X has a positive, and in this case, a statistically significant correlation with Y, and X2 is also positively correlated, although albeit not statistically significant in this case. But we're going to go into that in more detail when we're actually looking at the logistic regression. Okay, so now I'm going to scroll down. We're going to be looking at the case processing summary. So we're looking at this, and it's telling us that our sample size is n, and that there's no missing data. And because I didn't play around with the labels and create some kind of a story to go with this, it's just a 0 means 0, and 1 means 1 in the dependent variable coding. So now we're going to be looking at block 0. So because this isn't hierarchical logistic regression, there's just going to be 2 blocks. There's going to be block 0 and block 1. Where block 0 means that there are no predictive variables or independent variables, excuse me, in the model that are going to be depicted in this chart. So it's essentially an intercept-only model, or like the null. We're looking at the null, basically. So when we're looking at the classification table, we are in this model predicting that everyone is going to be 0. Oops. And what ends up happening is that 56 of them are 0 and 44 of them actually are 1. So when we're looking at our overall percentage, what this is saying is that if we predicted that everybody is 0, then we have a 56% accuracy rate of predicting the dependent variable out of the null model. When we're looking at the variables in the equation, we're just looking at the constant. We're not having any independent variables. And we're going to look at this a lot more when we actually have independent variables to look at in the equation, but we're going to be looking at the unstandardized B. We're going to be looking at the walled, the significance of the walled, and the exponentiated B. So the walled statistic is a significance value, and it tells us basically whether or not we want to reject the null in this case. So if the significance value is greater than 0.05, that means that we're failing to reject the null, that there's a statistically significant difference between these scores. And the exponentiated B, which is our odds ratio, is basically, it's not basically, again, it is a ratio of our probability of having a 1 over our probability of not having a 1. So in this case, it's 44 divided by 56. So 44 divided by 56 will get us 0.7857, which is this number right here. And then the variables that are not in the equation that are going to be in block 1 are x, which in this case is statistically significant, and our x2, which in this case is not. So now we're going to delve more into that in block 1. So this is including our predictors now into the model. So we want to see if there's any statistical significance in the model with the chi-square. So when we're looking at our omnibus test of model coefficients, we're really looking at this right here. And we're testing the hypothesis that the independent variables have some ability to predict our dependent variable. And since the chi-square value is statistically significant, we can feel confident in saying that there's at least something worth looking at with our independent variables. So we're going to take a closer look further down. In our model summary, and I'm just going to butcher the names of all of these things. The Naglikerke R squared is basically a pseudo R squared. Sorry. It's on a 0 to 1 scale, and this is often interpreted because it's on a 0 to 1 scale, and a lot of times how people would interpret this is like about 28.4%. You can kind of look at this number right here, of the variance in the dependent variable can be explained by the independent variable. It's not really R squared, so that's all I'm going to say about that. And I'm going to talk a little bit more about this Hosmer and Lemichaud test. So in this test, we want the significance value of the chi-square not to be statistically significant. So we want it to be greater than 0.05. And that means that the model does a good job of predicting the dependent variable. So if it's less than 0.05, if it's statistically significant, then it indicates that there's something not quite right about the predictive capacity of the model. And then the only other thing to kind of talk about with the chi-square of this is that it's really sensitive to sample size. So 100 in our sample is not particularly large, which doesn't affect this, but it is just good to know that the chi-square is affected by the sample size, in that smaller deviations of smaller sample sizes are going to have more of an impact. And so just something to kind of be aware of. So when looking at this classification table for block 1, we want to compare it to block 2. So kind of we're going to go up really quickly and look at block 0 and see that we originally predicted in the null that everything was going to be 0. 56 were, 44 weren't, and our percentage, or overall percentage, was 56. So going down to this classification table, we can see that we predicted that 48 were going to be 0. And of that, 19 were, and so far we can read the rest of the table like that. I'm not going to go into every single possible block. But what is really important is that our overall percentage is higher in our block 1. So this means that in this block we had a 73% accuracy in predicting our dependent variable. So if we want to know if this is statistically significant, this change in our overall ability, we're going to be looking at the significance values of the WALDs. So sorry, I'm starting to lose my voice. So we're looking at the X. We're seeing with our unstandardized B that it is positive correlation, and we're going to be looking at our WALD score, which is significant. Sorry, so if it's positive, if our independent variables are positive, sorry, if our unstandardized B's are positive for our independent variables, then the greater the value in our independent variable is associated with a greater probability of higher the higher dependent variable value. So in this case, 1, since it's dichotomous, it's just 0 and 1. And with our exponentiated b, the odds of it being 1, of our dependent variable being 1, are 1.053 times more likely than our odds of our dependent variable being 0, and that's controlling for x2. So that's really important because even though our x2 is not statistically significant in this case, our model is accounting for it. And as we talked about earlier with Karina Mood, her article, that accounting for all of the independent variables possible is going to be just really a lot more important with logistic regression. So accounting for that is in this model is going to make the x a better predictor of our dependent variable. So we don't have any standardized beta weights to compare like we do in multiple regression, but we're going to be using our exponentiated b in this case to do the best that we can. Okay, I feel like I covered most of the things that I was hoping to cover in this. Feel free to let me know, as always, if there's any gross, I was going to say gross negligence, but hopefully not, just like big things that I missed, and I would be happy to cover them. Thank you again for all of the work that you guys have put into the semester, and I bid you adieu.